These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So here's a function that you and I have not discussed yet. Do you know how to solve this problem? Make sure you study the problem carefully. How would you solve this? Tell me what the answer is here.
Okay. Natural log of x is equivalent to 1 over... let's look at my formula sheet, because we just touched on this in class today.
Make sure you've studied the problem. What's the question asking you for?
The function of x at 4.
That's right. So is it asking you for the derivative?
It's not.
But I think you're looking at your derivative sheet. So it looks like you're getting ahead of yourself. Do you know how to figure out then this, the function of 4?
We take the natural log of 4.
Okay, good. Go ahead and try that and tell me what you get.
1.386.
Okay, good. So the main thing I wanted to do there is just make sure that you knew how to do that on your calculator. So that would give us 1.39, like you said. Okay, good. Remember also to distinguish between the function and the derivative. That might not be too crucial for this mastery test, but it's crucial for our understanding. Okay. So let's try this problem.
Okay. Natural log of 5 plus 8, 9.61.
So were you taking the derivative?
No.
No, I just wanted to test again. This was not a derivative problem. This was just making sure you know how to take natural logs. So what does ln stand for?
The natural log.
Natural log, I gave it away. Okay, so that's just a new function that you and I haven't worked on yet. So it's important to know how to do those on the calculator. So I'll go back to here. Okay, now you said you just started covering this. Do you know what the rule is for finding the derivative here?
I know it's 1 over... It's 1 over x.
That's right.
That's right.
Okay, so we need to memorize that. That's just a whole new derivative rule. So that's a new derivative rule that we haven't talked about yet. This is just like, remember that we had to memorize how to find derivatives of sine, cosine, and tangent? Well, we need to memorize how to find the derivative of the natural log as well. This is a derivative that will be very important for the whole rest of your course. This is a very important function, so we'll keep coming back to that. So this has to be memorized. Now, as usual, this rule only works if x is a single variable. If we're taking the natural log of a single variable, we can use this rule to find the derivative. If you're taking the natural log of an expression that involves x, then we'll need more techniques. This rule only works directly when you're just taking the natural log of a single variable, just like the trigonometric derivatives that we learned before. Okay, so let me give you this problem. Okay, so let's try this problem.
Okay.
Okay, looks good. Let's check that on your calculator. Talk me through how you would do that.
Okay, so we could use a value so we can double check. So let's use 5, and we'll solve for it first. So in the calculator, I'm going to plug in. I'm going to go with math, then to option 8, and then to x cubed plus natural log of x, close parentheses, comma, x, comma, 5, closed. And I get 75.20.
Okay, good. Notice that the answer, you know that the answer is exactly 75.20, but when you use the derivative on your calculator, it said it was 75.200000101, something like that. Is that what you got?
Mm-hmm.
That's just
Yep.
because your calculator actually only can approximate derivatives. Your calculator doesn't actually know how to do calculus. It's using an approximation method. So it shouldn't surprise us if the answer sometimes just comes out to be only approximately what we know it should be. But so does it look like we got this right?
Yep.
Yeah, we did get it correct. Okay, good. Okay, good. So we did that correctly. Very good. And that's the correct method for checking it on the calculator as well. I'll write down another problem on my screen. Notice that on this problem, you combined our new derivative of the natural log with just the way to find derivatives of sums, which we know works pretty simply. All right, let's try this problem. Did your homework involve natural logs?
No.
Oh, okay.
Oh. Yeah.
Okay, that surprises me because I thought you had said that the homework had covered material we hadn't gotten to yet. Well, I guess maybe it had some like word problems type stuff that we haven't been working on.
Right. There were some word problems and some problems with finding equations of the tangent line.
Right, yeah, we've been skipping over that because that won't be on the mastery test.
Right.
Okay, fair enough. All right, so let's try this problem.
Uh, okay.
Okay, I'll go back to my screen. Now remember, here's the rule for the derivative of a natural log that we were talking about before. Here's the rule for the derivative of the natural log. Do you remember when we were talking about this a few minutes ago? I mentioned something that maybe you might not have quite known what I was talking about, but I said this rule for taking the derivative of the natural log, it only works if you're taking the derivative of a single variable. This does not work if you're taking the derivative of a function of x. Do you understand what I mean by that? So, does that make any sense?
Yep.
Yeah. So for example, can we use this simple derivative rule here to find the derivative, to find this derivative? Could we use this simple rule to find the derivative of this function?
Of the function of log of x. Yes.
Yeah. Could we find the derivative of this function?
Yes.
Yeah. Could we find the derivative of this function?
Yep.
Could we find the derivative of this function?
No.
No, because now we're not just taking the log of a single variable. Could we find the derivative of this function?
Yes.
Well, no, because this rule only works if you're simply taking the derivative of a single variable, not when you're taking the derivative of a function of a variable. Maybe you said yes because the w only appears once, but it's a little hard to put this into words. This rule only works when you're just taking the derivative of a single variable by itself. If you're taking the if you're taking the natural log of a single variable by itself, if you're taking the natural log of the function of a variable, then this rule doesn't work anymore. So would the simple rule for taking derivatives work on this function?
No.
No. How about on this function?
Yep.
Do you know what this symbol stands for here?
Z
Yeah.
squared.
Okay. I'm not quite sure why you said yep. Remember, we were saying that the rule only works if you're taking the if you're taking the natural log of just a single variable by itself. It doesn't work if you're taking the natural log of a function of a variable. So it doesn't work here because we're not just taking the natural log of z, we're taking the natural log of a function of z. Maybe I'm having a hard time expressing this idea. Once we understand what I'm trying to say, it's a pretty simple idea. So these are examples where the simple rule works. And these are examples where this simple rule doesn't work. So could we use this simple rule for taking the derivative of a natural log? Could we use it on this function?
No.
No. How about on this function?
No.
No. How about on this function?
Yes.
Yeah. All right. Well, you can see that it's hard to put this into words, but there's just got to be a single variable and nothing else inside of the natural log in order to use the simple rule. If there's any type of complicated function inside of the natural log, this simple rule does not work. So let's go back to the example that I was discussing with you here. Here's the example you were just trying. So does the simple rule work directly on this problem?
No.
No. But we have gone over techniques that you should be able to use to adapt here. So give this another shot. There should be a way to combine the various techniques we've talked about so far to figure out an answer here.
Okay.
Okay, so you saw what I was getting at. We were able to use the chain rule here. Good. I kind of briefly mentioned this before. One of the most common mistakes people make in calculus is not realizing when they need to use the chain rule. Oftentimes people try to do problems using simple rules when they need the chain rule. So the original function here was natural log of x cubed plus 1. Does our simple rule for finding the derivative of natural logs apply to that function, natural log x cubed plus 1?
No.
No, because it's not just taking the natural log of a single variable. What was the advantage of using the chain rule? Well, when you use the chain rule, you got a new function, natural log u. Does our simple rule for taking the derivative of natural logs apply to that new function, natural log u?
Yep.
Yeah. Oh, but I think you didn't actually do it. You didn't actually take the derivative of the outside.
Derivative of line of u is 1 over u.
Good. But we've actually skipped a step. We don't want to do that. So go back and erase the 1 over x cubed plus 1. Erase the 1 over x cubed plus 1 so we can do this step by step. All right. So what is the derivative of natural log u? That's right. That's the step we were skipping. So that's now you're actually using the rule for derivative of natural log. Do we need to put a prime outside that parenthesis?
No.
No, because we've just taken the derivative.
Okay.
Okay, so the first time we used the chain rule, we made a mistake on that. Okay, so we have to be careful about that. In fact, I think the mistake you made was one we've seen a couple of times. Instead of taking the natural log of u, you just rewrote natural log of u. But remember, most functions are not the same as their derivatives. So that for some reason, that seems to be a very common mistake that students make when they take the derivative. So oftentimes people just rewrite the function instead of actually taking the derivative. But remember, that never works unless you're working with the e to the x function. Okay, all right, so let's practice this some more. I'll go back to my screen. Let's try this problem.
Okay.
Okay, good. On your third line, it looks like you've written linu prime. Now, this function is actually not written as lin, it's just ln. Lowercase l, lowercase n. Okay, but other than that, that looks like that's correct. That's the correct approach for that problem. I'll go back to my screen. So what's the most common mistake that people make here? The most common mistake is thinking that this is the answer. Do you see how it would be tempting to say that this is the answer? This is the common mistake. People commonly forget that they have to go ahead and take, this is what you would get if you only took the derivative of the outside function. People forget that they also have to take the derivative of the inside function because they don't realize they need to apply the chain rule. So this would be wrong because we haven't applied, because we haven't actually taken the derivative of the inside here. How would you read this aloud? What does this say in words?
The function of x equals the natural log of 8 plus 2x to the fifth.
Good. Natural log of 8 plus 2x to the fifth, or you could say ln of 8 plus 2x to the fifth, but this is not line. It's not read as line, because what does the ln stand for? It stands for natural log. Okay, good. All right, and to save time, I'm not making you check all of these on your calculator, but I still do think it would be good practice to go back after the tutoring session and check all the examples we've done together on the calculator so that you can build up some speed at that. We don't have time for that in the session, but I think that would pay off for you in the course if you practice that skill. All right, so let's look at this. Let's try this problem. Looks like you need a new sheet, or will soon.
I would just leave it like this, but just to take a stab at it, is this that? Cosecant.
Okay, very good. Yeah, that is correct. You and I haven't talked about that, but it looks like you learned that on your own. 1 over sine of x really is the cosecant of x. That would be correct. If this was a test question, it would be better to not simplify and avoid the chance of making a mistake. But that's good to know. It's good that you went ahead and learned that. It's true. Cosecant of x really is just 1 over sine of x. That's a good point. You could also have actually said, this is also, would you agree that this is cosine x over sine of x?
I'm not sure about that.
Well, I mean, so you had 1 over sine of x times cosine of x, right?
Right.
If you multiplied that, you would get cosine x over sine x.
Mm-hmm.
That's also the cotangent of x. I don't know if
Okay.
you've learned that. Cotangent is cosine over sine, just like tangent is sine over cosine. Okay, but looks like those trig skills won't be too important for the mastery test. For the mastery test, it's better just to leave things in the form that we get. Okay, good. But what you wrote down there was correct. All right, good. That's a good application of the skills we've been talking about. So you can see how crucial the chain rule is. We're coming back to it now in this section. You did that correctly. That's good. I'll go back to my screen.
Okay.
Is this true or false?
That is true.
Actually, it's false. This is true. So I wanted to warn you about the difference between these two things. Do you see how these are different?
Mm-hmm.
Yeah, so it's very important not to confuse these two ideas. Is the natural log of x the same as 1 over x?
Yep.
No, that's this idea here. The natural log of x is not the same as 1 over x. The derivative of the natural log of x is 1 over x. The derivative of the natural log of x is 1 over x. That doesn't mean that the natural log itself is 1 over x. Those are two different things.
Right. I think I misspoke or
Oh,
misheard
okay,
you.
okay.
Okay.
So would this be true?
F of x equals the log, natural log of x, so f of x equals 1 over x. No.
That's right. How could I rewrite it so it's true?
Could write it as f prime of x equals 1 over x.
Okay, that's right. The natural log is not the same as the reciprocal of x, but the derivative of the natural log is the reciprocal of x. So it's important not to confuse the function and its derivative. Good. Is this true or false?
False.
It is false. How could you rewrite it so it's true?
The f prime of square root of x equals
How could,
1/2.
how could we write a true statement that involves x to the 1/2? What does x to the 1/2 equal?
Oh, x to the 1/2 equals square root of x.
That's right. It doesn't equal the derivative of the square root of
Right.
x. It's just the same, another way of writing the same thing as the original function. What is the derivative of the square root of x?
1/2 x to the negative 1/2.
Which you can see after we've written this line. Okay, so that's just more practice and how it's important not to confuse functions and their derivatives. Good. You hadn't been making that mistake, but I just wanted to warn you against it.
Okay.
All right, good. Let's try this problem.
Okay.
Okay, that looks good to me. Excellent. Good. That's a good approach for that problem. And again, we're not going to take the time to do this together, but it would be excellent practice to go back and check that on your calculator so that you're building skills. All the problems that we're doing together, if you can find the time, it would be good to try to check them on your calculator. All right. I'll write another problem on my screen. Let's see here. 1 second.
Just a side note, I took that quiz today, and I think I did pretty well. I think I got 100, so that's good.
Which quiz was that?
That was the makeup quiz for my third organic chemistry quiz, the one I botched on Friday.
Oh, you retook the OChem quiz.
Yeah.
Okay, good. Well, we'll see how that. But you haven't gotten the results back yet.
Mm-mm.
Okay, well, we'll see. All right, but that's good that it's good that it felt like you were doing well on that. Let's see here. All right, let's try this problem.
Okay.
Okay, that looks good to me. That's the correct method. Good. I'll go back to my screen. Let's try this problem.
log u ex product rule. So x times bx. Okay.
Okay, that's good. Good. That's a tough problem. You took your time and you did that correctly. That looks correct to me. One thing I would say is I noticed that when you started solving the problem, you did the chain rule and the product rule at the same time. And you did that correctly, but I think at this point in the course, it would be safer to split those up into two separate steps. You didn't make any mistakes here, but definitely on the test, it would be better to first write down the chain rule step and then write down the product rule. We've still just learned the chain rule, so it's better to separate those into two separate steps until you've had some more practice with them. But you did it correctly anyway. Okay, I'll go back to my screen. Also, in that last problem, you did a good job putting in the parentheses that you needed. You put in a big set of parentheses in your answer that were necessary for the answer to be correct. So that's good. You had a few more parentheses than you really needed, but it's better to have too many than too few. All right. Let's try this one.
Oh. 2 times x squared times 3x squared. Okay, I would just leave as is.
Okay. What do you have written in the denominator on the right side for your answer?
On the right-hand side, I have x cubed plus 1 squared.
Okay, looks good. All right, yeah, it is possible to simplify this sum, but I guess we don't need to do that for the test, so we'll leave it like this. Good. There actually is another technique you can use on this problem, but we haven't covered it. So for us, this would be the best approach. So yeah, that's a good approach. This is the first time we've combined natural logs with the quotient rule, so you did a good job on that. You did a good job separating out the chain rule step from the quotient rule step. First you did the chain rule, and then you did a separate step for the quotient rule. I think that's the best approach. So that was pretty complicated, but I think you avoided making any mistakes all the way through. So that's a good systematic approach. Good. I'll go back to my screen.
Okay.
Let's try this problem.
G of x equals x squared plus 1 natural log cosine of x. Okay. And g power of 0.
Okay, let's go back to my screen for a second. Do you think this is true or false?
It's false.
Yeah, now, this is a little tricky because you and I, we're under time constraints here. We haven't really discussed what the heck natural log means. I haven't told you what natural log means or why it's an interesting function or what the rules of it are. But anyway, you can't just assume that you can take the constant inside of the natural log. Unless we've learned a rule that says that that's legal, we're not allowed to do that here. So you can't just take the constant from outside the natural log and put it inside the natural log. How about this? Do you think this is true or false?
That's false.
Yeah, I mean, we haven't talked about this, but we certainly can't assume it's true unless we've learned a rule that says it's true. And it turns out it's false. You're not allowed to just take this number and stick it inside of the natural log. There's a difference between taking the log of 3 and then multiplying by 8, or first multiplying 3 by 8 and taking the natural log. There's no reason to think that we can put those inside of each other. It's like this example. Do you think this is true or false?
8 times sine of 4. That's false.
You're not allowed to just take this constant and put it inside of the sine. Now, here's what you might have been thinking of. Is this true or false?
That's true.
Yeah, this is true because we're not taking, there's no function here. But once we have a function, we can't just take the number inside of the parenthesis. So let's see what you tried to do here. Do you see why I'm mentioning that here? It seems like in your first step, you tried to take this x squared plus 1 and put it inside of the natural log. But we can't do that unless we've learned some rule that makes it legal. And in fact, it's not legal. There's no rule that allows you to just take something that's outside of the natural log and put it inside of the natural log. What made it feel like you could do that? I'm not sure. You might possibly have been thinking just of something like this that doesn't really have a function in it. Or you might have been thinking of something, I don't know, like this. Is this true or false?
That's false.
Careful, this one is actually true.
8 times 3x is 24x. Okay, yeah, that one is true.
Now, so what's the confusion here? So what does this mean in words?
The sine of 3?
That's right. What does this mean in words?
X times 3?
Notice that they're written very similarly, but they're totally different. They're written, they both have parentheses, but the parentheses mean totally different things. Here, the parentheses mean multiply. But do these parentheses mean multiply? We're not multiplying sine times 3. This is function parentheses. This means sine is a function of 3, and these are multiply parentheses. Well, when you're using multiply parentheses, you are allowed to take the constant and put it inside the parentheses. But when you're using parentheses that indicate a function, you're not allowed to take the constant. So that might have been what was in the back of your mind. You might have been treating this as if it was x squared plus 1 times natural log, times cosine of x. That might be what made it feel natural to move it inside the parentheses. But anyway, that first line that you tried to do, that turns out not to be legal. So go back and fix that. See if you can think of another way to solve the problem. I can see why that was tempting. See if you can think of some other legal approach to solve the problem.
Okay. Yep, we can just keep this.
Okay, let me back up with you a moment. Let's see. So you wrote g of x, then you wrote g prime of 0 equals question mark, and then you started solving the problem. So what justifies your third line? How did you get that third line?
Well, we have the chain rule right here.
Mm-hmm.
And then we have whatever this product of the chain rule is times this right here, which is going to be the product rule. So
Okay, so
I don't
tell
know.
me, so what were the rules? Tell me one more time. You basically just did, but let's clarify. What were the rules that you used to get to line 3? What are the names of the rules that you used?
Chain rule.
Good. Was the chain rule the only rule that you used, or did you use any other rules?
That was the only rule I used.
Let's see. I'm going to go back to my screen for a moment. So I've invented a new little problem to review our intuition here. Here's the problem. Is this line accurate or inaccurate? Is this a legal or an illegal step to go from here to here?
That's legal.
Any particular reason?
No, that's not legal. Okay.
How is it not legal? What's wrong about it? What should I do instead?
Because we have to use the product rule here.
That's right. So basically what you're doing here is you're hoping that the derivatives work naturally for products, but they don't, unfortunately. You can't just assume that the derivative of a product is the product of the derivatives. This line here is wrong, incorrect. And that's kind of what you were doing on the problem that you were just looking at. You were assuming that the derivative of the product would just be the product of the derivatives. Well, let's go back and see if we can fix that so that we're justifying each step.
I'm going. Okay.
So let's try to figure out what the next line to write down is.
Okay.
Okay, good. Let's write down for our notes what was the rule that justified that last step. Good. That would be a good thing to be in the habit of doing here. Okay, good. So now we're ready to move on. By the way, right now we're finding g prime of x, not g prime of 0.
Mm-hmm. That's not true. Okay. No, we're not taking derivative of this, so it doesn't matter. Okay. No, we are.
Yeah, we forgot to put in that prime. I missed that too. Good. Good. Let's write down what was the rule that we used in that step too.
Okay.
Do you know what the word quotient means in math?
Yeah, that's division.
That's right. Good.
Right.
So that can help us to remember when to apply it. And what does product mean?
We multiply.
That's right. So what's the rule that we just used?
Chain rule.
The chain rule. Okay, good.
Okay. I'll leave this as is.
That's fine with me. Okay. So are we done?
We are not, unfortunately. Okay, g prime of 0. Okay. So 0 times 0 plus well, negative sign of 0. Okay.
That's right. Okay, well, that one gave us some trouble. That would be a good one to go back and try again. So this problem that we just did, I took this from one of the sample mastery tests. So it looks like this is a hard problem, but it looks like your instructor expects us to be able to do this for the exam. Okay. Why did this one give us so much more trouble? Because before this, I think we were on a roll. Before this, we'd gotten a whole bunch right in a row. This isn't the first time that we've been using the product rule and the chain rule in the same problem. We've done a couple other natural log problems where we use the product rule and the chain rule in the same problem. So why did this one give us trouble? Well, here's why. When we did the problems before were problems where first we used the chain rule and then we used the product rule. Or first we use the chain rule, and then we use the quotient rule. The thing that messed up your intuition on this problem, I bet, is that and this was a problem where we had to see that we had to do the product rule first, and then the chain rule. I think we talked about that issue in one of the previous sessions as well. So that's something to watch out for on the test. If there's more than one rule that you're going to be using on a problem, not only do you have to decide what rules to use, but you also have to decide what order to use the rules in, and that takes practice. And also remember the product rule is a rule. You can't just say that the product of the derivatives is the derivative of the product. Derivatives don't work naturally for products. We actually have to use that rule. Okay, so now we have that written out with a good notation. So I'll go back to my screen and we can wrap up. All right, so I think now we've covered, anyway, that was a very hard problem. Before that, you were getting them all right. So I think we've made some good progress on natural logs. I think you basically got the idea for natural logs, except the really hard problems like that. So we'll put that a check mark next to that. But obviously, the next thing you should do is hopefully you have a bunch of homework problems that involve natural logs. So this would be a good time to go back and do a bunch of problems with natural logs. But remember, it's important to do problems that you can check your answers to. So if the homework is the even problems, it's important to try to find time to do a bunch of the odds too, to make sure that you're actually getting those right. Well, so let's try this problem on your screen.
Okay. Zero minus 0 plus 5. 0 minus 2. -2. Okay.
Okay, let's check that on your calculator. And you can talk me through how you're doing that.
Okay. Math. Option 8. Take the natural log of 4x cubed minus 2x plus 5, close parentheses. Yeah, close parentheses, comma, x, comma 0, close. Get negative 0.399 and 0.2 times -2 is negative 0.4. Yep.
Good. We talked about how when you use your calculator to find derivatives, it's actually really only going to give you an approximate answer. So it shouldn't worry us that those two answers are not precisely the same. Okay, good. So what is the exact answer?
The exact answer is negative 0.4.
Good. How would you interpret that? How do we interpret that answer?
Okay. As the value of x increases from 0 to 1, the value of the function is going to decrease by negative 0.4.
Excellent. Great. Which function is that? Which function will decrease by negative 0.4?
The function at 0.
Which function? what function at 0, what function is going to be decreasing? What's the function that you said would decrease by negative 0.4?
Slope of the tangent line.
Okay, so what you said was correct. It might be that you didn't quite understand what I was asking you. I just want to make sure that we're thinking of the right thing in our mind. So you said that when you increase x by 1 unit from 0 to 1, there's some function that's going to decrease by negative 0.4. But there's a million billion functions in the world, right? There's f of x equals sine x, there's f of x equals square root of x, there's f of x equals natural log of x plus e to the x squared. What is the function that's going to decrease by negative 0.4 units when we increase x from 0 to 1?
It's the natural log of 4x cubed minus 2x plus 5.
Okay, that's right. Yeah, you might have already understood that, but I just wanted to make sure we were clear about that. Because after all, there's two functions that you have written down. You have f of x written down, and you also have f prime of x written down. Well, the negative 0.4 doesn't tell you how f prime of x is going to change. It tells you how f of x is going to change. I think I'll go back to my screen for one. No, let's actually stay on your screen for a second. So let's say that we increased x by 2 units from 0 to 2. How would the function change then?
The function would decrease by a total of 0.8.
Good. We should be saying that it would be approximately negative 0.8.
Okay.
And that the approximation probably wouldn't be as good as when x changed by a smaller amount. Okay, good. So now what's the graphical interpretation of our derivative here?
Okay, the graphical interpretation is as x moves from 0 to 1, the slope at 0 to 1 is negative 0.4.
Okay. Now I think there we're mixing up the two different interpretations. There's a cleaner way to say what we were just talking about. The graphical interpretation is the derivative tells us the slope of the tangent line to the function. The derivative tells us the slope of the tangent line to the function. So what I was going for is at x equals 0, the tangent line to the function has a slope of negative 0.4. I know this won't be on the test tomorrow, but these are ideas that are going to be very important going on, so we may as well try to keep reviewing those as we continue. Okay, so I'm going to go to my screen. So for the example that we just did, to understand that interpretation, we could say that the function was natural log of 4x cubed minus 2x plus 5. So I put that in here in the functions list, natural log 4x cubed minus 2x plus 5. Then I could graph that. And maybe I'll zoom in on the point where x equals 0, since that's what we were focusing on.
Log of 4. Huh. Yeah.
Are you trying to follow along on your calculator?
Yeah.
So I'll go back to my y menu so you can see what I did there. So you go to the y equals menu and you type in this function.
X cubed minus 2x plus 5. Yeah, I have that.
Good. And then you hit the graph button.
Yeah. It says error window range.
Oh, all right. Well, go to zoom and maybe set your zoom back to standard 6. And then go to graph. Do you get a graph then?
Yes, sir. Yeah.
Excellent. Okay. So you must have had your window defined for something where the function didn't exist, perhaps. But you can always go back to the standard window by going to zoom standard here. So you have a graph that looks kind of like this?
Mm-hmm.
All right. So anyway, So that tells us that the graph looks kind of like this. So here's the key thing. How do we put in our graphical interpretation? Well, remember we're focusing on x equals 0. So that's this point here. And I could draw the tangent line at this point. So remember we got this number 0.4. What does this negative 0.4. What does that number negative 0.4 describe in this graph?
That's the slope of the tangent line.
That's right. It's the slope of this line is 0.4. The slope of this line everywhere is 0.4. The tangent line at x equals 0 has a slope of negative 0.4, I should say. You could also say the slope of the function is negative 0.4, but it's kind of hard to define what you mean by the slope of a function without using the concept of the tangent line. By the way, one thing that you notice here is how is this reflected that this slope is negative? Well, does this look like a line with a negative slope?
Mm-hmm.
And you can even see from your graph here, notice at this point is the function increasing or decreasing?
It's decreasing.
And that corresponds to this negative slope. That's one of the main things you're going to focus on the next chapter of your textbook, how to interpret the derivative. If the derivative is negative, that means that the slope is negative here. So by the way, what do you think the derivative would be at this point? Positive or negative?
It would be positive.
And how about here?
It would be positive.
You could check that out as homework. You could plug in bigger numbers for x and see that the derivative comes out positive here and positive here, but there's a section where it's negative. And do you see, you can use this tangent line to approximate the function. How much does the function change if we increase from 0 to 1? Well, this is how much the tangent line changes. You can see that for small changes, the tangent line is almost smack dab on top of the graph of the function. In fact, you can hardly tell the difference between them. So for small changes, the tangent line tells you the approximate change on the function. On the other hand, if you wanted to know how much the function was going to change if you went from 0 to 5, notice it's not a very good approximation anymore. At this point, the tangent line is a long way away from the function. So how would I label this line? This line is the tangent line. How would I label this curve? What does this curve represent?
That's the function?
F prime or F?
That's f of x.
Yeah. So we could say this is f of x, and this is the tangent line to f of x at x equals 0. Okay, so this is all stuff that you're going to be working with all the time in the next chapter, but it's good at this point, even when we're mainly focusing on the mechanics, to know in the back of our mind what we're doing. Again, if you can find the time, it would be good practice when you're doing these problems to get into the habit of graphing the functions and then actually looking where the tangent line is and seeing if it matches the answer. You should see that when the derivative comes out negative, that's because the tangent is downward sloping, and when the derivative comes out positive, that's because the tangent is upward sloping. The more you're able to practice that and get a feel for derivatives, the easier the next chapter is going to be, which is more types of word problems and understanding. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.